Picture this. You're walking down a quiet street, coffee in hand, when, without warning, the curb in front of you zips 2.5 meters to the right. Not a slow creep, a snap, faster than city traffic. The painted centerline that used to be straight, it now looks like a badly shuffled puzzle. Wild, right? Here's the thing. This isn't a thought experiment. A security camera actually caught that exact moment on the Sagaing Fault. No seismometer graphs, no artist renderings, just raw video of Earth doing a sideways shrug. First, let's unpack what we're seeing. 1. The fault let go in a single violent burst, a slip pulse. 2. That pulse ripped past the camera in just seconds. 3. It left behind a textbook-perfect 2.5-meter offset we can measure frame by frame. Let that sink in for a second. Why does this particular clip make geologists giddy? Because for the first time, we can clock exactly how fast the rupture front traveled, how far each slab moved, and even how the motion ramped up and then faded. Think of it like finally having slow-mo replay for a play that decides the championship game. Except the playing field is 160 kilometers long and made of rock. Now, what did the footage reveal? The key point is that almost all the action was squeezed into that compact slip pulse. Instead of several seconds of grinding, the ground behaved like a razor-sharp blade. Fast, focused, unforgiving. Anything crossing the fault, roads, pipes, fiber optic cables, got maximum strain with minimum warning. Picture a buried water main. If the ground crawls, the pipe might bend. When it snaps like this, it shears clean off. That's the difference a slip pulse makes. Second, the camera captured timing. Because the lens sat only a few meters from the break, scientists can chart the entire motion millisecond by millisecond. Those numbers drop straight into engineering models. Instead of guessing how a bridge deck might respond, designers can match steel and concrete against real-world shake, right down to acceleration curves. And there's a twist, literally. A subtle 6-degree bend runs through this stretch of the Sagaing Fault. Even that gentle kink reshapes stress, steering the pulse like a curve in a racetrack. By mapping bends and jogs in detail, planners spot places where shaking might spike, or surface cracks could hopscotch into new neighborhoods. If your city straddles that zone, that's need-to-know intel. Third, the single clip plugs into the bigger puzzle. Satellite deformation maps, seismic inversions, field surveys, all of them give pieces of the rupture. Tie those to this pinpoint video, and you get a stitched, high-resolution picture of which sections slipped hard, which barely moved, and where strain now lingers. That, in turn, sharpens forecasts. Which neighboring strands might pop next, how often, and with how much force? Think of it like reading an old scar. Slip pulses can leave fingerprints deep underground, tiny zones of pulverized rock that mark where stress once focused. If geologists find those scars in older layers, they may realize, hold on, this fault fired off quick bursts before. That could upgrade hazard levels in regions with no living memory of big quakes. And here's where it gets exciting for the rest of us. Security cameras, doorbells, even car dash cams are turning into a planet-wide video array. The next rupture could be captured from 20 different angles, giving an almost 3D movie of the ground tearing. Each clip tightens the feedback loop. Better data, better designs, safer cities. So quick gut check. 1. Do you actually know which fault is closest to your home, office, or daily commute? 2. If the floor could shift 2 meters in the blink of an eye, what 3 things in your space would worry you most? Bookcases, gas lines, that giant TV? Which one will you secure tonight? 3. Who are the 2 or 3 people you'd need to reach if cell towers went down? Do they know the plan, the meeting spot, the go-bag location?
So here's what we covered today. First, a security camera showed us Earth's raw power, a 2.5-meter sideways lurch caught in real time. Second, that footage revealed a razor-thin slip pulse, the geological equivalent of a knockout punch. Third, a tiny 6-degree bend proved small kinks can supercharge stress and change how a rupture runs. Fourth, Combining one clip with satellites and seismology builds a crystal clear map of where strain still hides and where the next break may start. And finally, cheap cameras everywhere mean the next quake will be documented even better, turning disaster footage into life-saving design data. You now know the ground can move farther and faster than most of us imagine, but you also know science is catching up, giving engineers, city planners, and yes, regular folks like you the insight to act. So tighten that bookshelf, learn your local fault, and share an emergency plan with the people you love. Because the Earth will redraw its lines again. The question is, will we be ready when the camera starts rolling?